Okay, next we're going to talk about how to analyze the data from a Latin square design, and in particular how to do the calculations to perform the analysis of variance. Now before we go into that, I want to go back here and say one more thing about the layout for the Latin square design. So we'll first look at this canonical representation, this initial canonical layout for the Latin square design. And you'll notice that the structure of this square has the property that each treatment occurs once and only once in each row and column. All right, so if we look at row 1, A occurs only once, B occurs only once, C occurs only once, and D occurs only once. The same thing can be said for each of the other rows. There's no row where A occurs twice or 3 times or whatever. There's no row where B occurs more than once, and so forth. In addition, that property holds for each of the 4 columns. So in column 1, A occurs once, B occurs once, C occurs once, and D occurs once. If we look at column 4, A occurs once, B occurs once, C occurs once, and D occurs once. That is true for each of the 4 columns. And so this is the property of a Latin square itself. All right, it has that particular property. Now, let's look and see what happens after we randomize. And so let's go and look at the table after we've done both the row randomization and the column randomization and reorganize them accordingly. All right, and so we get to the place where this is what we would use to assign the treatments to the actual physical experimental units in the table. And so you can see here that that Latin square property is preserved. In the first row, A occurs once, B occurs once, C occurs once, D occurs once. In row 2, A occurs 1 time, B occurs 1 time, C once, and D once. And so the same thing is true for all 4 rows. In addition, that same property holds for the columns. So in column 1, A occurs exactly once, B occurs exactly once, C and D both occur exactly once. Each of those 4 columns, as you can see, have the property that each of those 4 treatments occur exactly once. There's no row, there's no column where a treatment shows up more than once. And this is this organizational strategy that allows us to account for 2 extraneous sources of variation, and then when we do the analysis, we can perform treatment comparisons, either via pairwise comparisons or more general contrasts, in such a way that the variability due to the row blocking factor and the variability due to the column blocking factor gets filtered out, it gets subtracted out. And so that's what gives those kind of analyses greater power and greater precision. So that's a very important characteristic of the Latin square design that I wanted to make sure that you were aware of. And so now let's look at how to analyze the data from a Latin square design, and in particular to perform the calculations that allow us to construct the analysis of variance table and test the analysis of variance hypothesis. And so in order to analyze, first summarize data and then analyze that data from a Latin square design, in this case we're actually going to need 2 summary tables. As we start looking at these more complicated designs, going from the completely randomized design, then to the randomized complete block design, and now to the Latin square design, these are more complicated, more structured designs, and that greater structure requires that we have a little bit more complicated summarizations as we increase in the complexity of the design. And so the first table for the Latin square design looks like this. And so you can see here in the body of the table, we've got the actual data represented here, the actual observations, the y sub ij's. Notice that we have not included that k in parentheses or square brackets. Remember, we said that was really not necessary because the actual treatment that is applied in a particular cell is a function of or determined by the I and the j, the row and the column. And so, in addition, at this point, notationally, we really wouldn't know which treatment has been assigned here in terms of the notation. So it's easier just to leave that K off here so that we don't clutter up the notation. Okay, so we've got in the body of the table, we have the actual data, the observed data. And then we have column totals. Okay, so these are the column blocking factor totals. And we also have the row totals corresponding to the totals for the row blocking factor. All right, and so we're using the standard notation here for these totals. We have the sum of the observations, and then also for the column totals, I've included the uncorrected sum of squares. We only have to have it really for either the rows or the columns. We don't have to have it for both. All right, so it suffices to do it for the columns. So the uncorrected sum of squares for column blocking factor 1, all right, that's what that cell represents, and so forth. So we've seen this type of summarization before in both the randomized complete block and the completely randomized design, and that carries over to the Latin square design, because we obviously do need to be able to calculate the total, the uncorrected total sum of squares, which is given by the row total or the row sum of that last row, right? And so that's what that represents. Now the second summary table that we need is a summary table that gives us the sums and the means for the treatments, all right? And so for treatments 1 through P, we would be able to calculate the total of the observed values for that particular treatment, T1, or treatment 1. And what we're going to do here is a common type of notation. For the treatment total, we're going to use the capital T for total. So this would be the total observed value of treatment 1 across the entire experiment, across the P observations would be T1. T2 is the total of the observations receiving treatment 2, and so forth up to T sub P, the total of the observations that have received treatment P. And then we can also calculate the means of the treatments, the sample means of the treatments. And so Y bar 1 would be the average of the observations for the experimental units that have received treatment 1. Y bar 2 is the average of the observations from the experimental units that have received treatment 2, and so forth. And then finally, over in this last column, we have the overall treatment total, the overall sum of the observations. All right, that's what that is, Y dot dot. So that's the sum of all of the observations in the experiment. And then we have the overall mean, all right, for all of the data in the experiment, Y bar bar. And so we've seen that notation as well. All right, then we calculate the row and the column summary statistics. And so again, this was represented in the table. In that first summary table, we have both the row totals and the column totals. All right, and so those are represented in that table. We also need the treatment summary statistics. All right, so the T sub Ks, and this is just one way of representing how to get that treatment total, the total for the observed values for the experimental units that have received treatment K for each K going from 1 to P. All right, and so you may be familiar with this type of notation or you may not. So let me just take a minute here and explain it. So notice that I'm summing over all of the experimental units, all of the cells in the Latin square table for the experiment. I going from 1 to P, J going from 1 to P. All right, and so here each term of the sum is a Y sub ij, the observation is in row I and column J of the table, times this function I. Well, this function I is an indicator function that takes on a value either 1 or 0. Okay, and as it's defined here, this indicator function is going to be 1 if the treatment, and remember this capital K is a function of I and J. It's the position. It's the function of the position in the table, row I and column J. So what this is saying here, it's an indicator function that's evaluated at this argument, and the argument is that capital K evaluated at I comma J, that position in the table, is equal to little k, where k is the particular treatment that we're talking about. And so what this means is that if the cell in the table at row I and column J received treatment K, then this indicator function is 1. If that cell got a different treatment, then this indicator function is 0. And so when you multiply that 1 or that 0 against Y sub ij, then the product is either going to be Y sub ij or it's going to be 0. It will be Y sub ij if the treatment in that cell was in fact the kth treatment, and it will be 0 otherwise. And so this is just a convenient mathematical way, although it's a little bit cumbersome to look at, but it's a convenient mathematical way to add up only those observations that received treatment K in the experiment. So that's why that gives us the total of the observations for the experimental units that received treatment K. Now, an easier way to describe T sub K is that T sub K is the sum of the observations for the experimental units that have received treatment K. So intuitively, it's very obvious. Mathematically, this is a little bit cumbersome, a little bit kludgy to look at, but sometimes we do need this kind of a representation when we start doing the mathematical manipulations. When we start doing the mathematical manipulations, sometimes having a formula like this is easier to use than trying to implement this particular intuitive description. Okay, so then once we have the treatment totals for each of the P treatments, we can use those to come up with the treatment means. And obviously the way that we would do that would be to divide the particular treatment total by the number of observations that went into that total, which is going to be P, assuming we don't have any missing data. And so that is how we would get the sample means for each treatment. Let me back up just a second here. Notice the one thing I haven't listed out here. I have not listed out the uncorrected sum of squares, but you've seen how to calculate those in the past. They are listed here in this first summary table, so I just did not bother to create an additional slide for that. I don't really think it's necessary to do. But we do need a value from, or that results from those uncorrected sum of squares, and that is the uncorrected total sum of squares, which again, let me scroll back here, that is given by this entry in the table. So you just have to remember to do these, calculate the values in this last row, and then calculate their total. All right, so once we've got these various summary statistics, the row and column summary statistics, the treatment summary statistics, then we can start doing the calculations to get the sums of squares for the ANOVA table. Now, as is usual, we first calculate the correction term, denoted by C, and that is equal to the square of the sum of all the observations in the experiment divided by the total number of experimental units, or the total number of terms in that sum, and that total is P squared. So that is how we get the correction factor. Now, once we have the correction factor, we use that in getting the rest of the corrected sums of squares. And so to start off with, the total corrected sum of squares, SS tot, is equal to the difference between the uncorrected sum of squares tot and the correction term, the correction factor. We also need the row sum of squares, and so we will denote that by SSR, and that is given by this expression here. All right, so 1 over P times the sum, I going from 1 to P. Here we're squaring the row totals and adding those up, and multiplying that sum, the sum of the squared row totals, by 1 over P, and then subtracting C. So 1 over P times the sum, I going from 1 to P, of Y I dot squared minus the correction term C. To get the column sum of squares, which we will denote by SSC, that is equal to 1 over P times the sum J going from 1 to P of Y dot J squared minus C. Here we are adding up the squared column totals. We are multiplying that sum of squared column totals by 1 over P, and then from that we're subtracting the correction term C. Okay, then to get the treatment sum of squares, SST, we square each of the treatment sums. We add those squared treatment sums up. We multiply that sum of squared treatment sums by 1 over P, and then from that we subtract off the correction factor C. And then once we have the total sum of squares, the sum of squares due to the row factor, the sum of squares due to the column factor, and the sum of squares for treatments, then we get the sum of squares error, SSE, by subtracting SSR, SSC, and SST from the total sum of squares. All right, this is the structure of the ANOVA table for the Latin square design. And so you'll see that this looks somewhat familiar, somewhat similar to the ANOVA table for the randomized complete block design, but we have one more row. We're going to have a row for each source of variability that we're accounting for. Now, in the randomized complete block design, we just had above the treatment row, we had a row for blocks, but here in the Latin square design, we essentially have two types of blocking factors, the row blocking factor and the column blocking factor. So we have a row for each of those. In each case, we have p rows, and so there are p minus 1 degrees of freedom. We have p columns, and so we have p minus 1 degrees of freedom for columns. We have p treatments, and so there are p minus 1 degrees of freedom associated with treatments. We have p squared total experimental units used in the experiment for a single square. This is for a single square. And so we have p squared minus 1 degrees of freedom overall. And then we have p minus 1 times p minus 2 error degrees of freedom. All right, and then once we have the degrees of freedom, and once we have the sum of squares, we calculate the mean squares in the usual way. We divide, to get a particular mean square, we divide the corresponding sum of square by its degrees of freedom. And so to get the mean square for rows, we divide the sum of square for rows by p minus 1. To get the mean square for columns, we divide the sum of squares columns by p minus 1. To get the mean square for treatments, we divide the sum of square for treatments by p minus 1. All right? And then to get the mean squared error, we divide the sum of squared error by its degrees of freedom, p minus 1 times p minus 2. Now I see I've got a typo there. Let me fix that real quick. And voila, there we go. That's fixed. All right, and then in order to get the F statistics, we divide the mean squares for that particular row by the mean squared error. And so to get the F statistic for rows, we divide MSR by MSE. To get the F statistic for columns, we divide MSC by MSE. And then to get the F statistic for treatments, we divide MST by the mean squared error. Now, the reason we divide each of these by the mean squared error is shown here in this table of expected mean squares. You can see here that the expected value of the MSE, the mean squared error, and let's focus here on the mean squares for a fixed effects model where we're assuming that the treatment effects are fixed effects. And so you can see here that the expected value of the mean squared error, MSE, is always going to be sigma squared, which is the variance of the error term. The expected value of MST, the mean square for treatments, is sigma squared plus a quantity that is going to be 0 if and only if all of the taus sub k's are 0. If any of those tau sub k's is non-zero, then when we square them, we get a positive value. And so this quantity will be positive. And because the tau sub k's, under the particular parameterization that we're looking at, the tau sub k's sum up to 0, if at least one is non-zero, then you know that there are at least two, right? So if any of the tau sub k's are non-zero, then the expected value of MST is going to be something larger than sigma squared. And so if we want to test the hypotheses that the taus are all 0, then the appropriate way to do that would be to form the test statistic by dividing the MST by the MSE, and that's based on an evaluation of these expected mean squares. Similarly, if you look at the expected value for the mean square for rows, you can see that the expected value of MSR is sigma squared plus something that's positive. P is going to be positive. Sigma squared sub rho will be greater than or equal to 0. Right? If sigma squared sub rho is 0, then the expected value of MSR is just sigma squared. But if there's any variability at all due to the rho blocking factor, then the expected value of MSR is going to be something larger than sigma squared. And so that is why this will be an unbiased estimator of sigma squared if and only if sigma squared sub rho is equal to 0. So that's why we divide the MSR by the MSE, all right, to get that F statistic. And the same reasoning applies to why we divide the MSC by the MSE right, to get the test statistic for evaluating the effects of columns. And so that's where we get those. Okay, the same kind of rationale applies if the treatment effects are random. The first two rows are going to be the same because in either case, the row blocking factor and the column blocking factor are assumed to be and treated as random effects. If in the experiment the treatments are random effects, then instead of having the expected value of MST involving unknown constants, the tau sub k's, it involves the variance term associated with the treatments, sigma squared sub tau, and it looks just like these other situations. And so again, even if treatments are random, to get the appropriate F statistic, we would divide MST by MSE. And that's what we're kind of explaining here on this slide. If the fixed effects, or in the fixed effects model, all right, so in other words, where the treatment is a fixed effect, the F statistic follows the F distribution if and only if the sum of the squared treatment effects, the tau squared sub k's, if the sum of those is equal to 0, which is true if and only if every treatment effect is 0. And so for that reason, the hypotheses that are being tested by the F statistic for the fixed effects model is given by these hypotheses here. So the null hypothesis, and again, let me back up just a few slides. And so this test statistic here, F sub t, all right, which is the mean square for treatments divided by the mean squared error. All right, so again, for a fixed effects model, the null hypothesis that is being tested by that F statistic is that all of the tau sub k's are 0, all right, against the alternative hypothesis that at least one of the tau sub k's is non-zero. And obviously we know that if one is non-zero, there's got to be at least one other one that's non-zero, all right? Now, so these are the hypotheses expressed in terms of the effects model representation. We can also think of this in terms of the means model representation, still thinking about this as a fixed effects treatment, all right? And so the null hypothesis in that representation, in a means model representation, would be that the population treatment means are all the same. There are no differences among the various population treatment means. Against the alternative hypothesis, that differences do exist among the treatment means. At least one of the population treatment means is different than the others. So that is what these are the hypotheses that are being tested with that treatment F statistic, right? If we are dealing with a fixed treatment effect model. Now, if we have a random treatment effect model, it's the same type of thing, but the hypotheses are expressed in terms of a variance component rather than the unknown population treatment means. And so in a random effects model, the F statistic follows the F distribution if and only if the variance, the variability associated with the random treatment is equal to 0, right? And we saw that based on the expected mean squares table. And so the null hypothesis being tested by that very same test statistic, but in the context of a random treatment effects situation, the null hypothesis is that sigma squared sub tau is equal to 0 against the alternative hypothesis that sigma squared sub tau is greater than 0. So if sigma squared sub tau is equal to 0, then there's no variability among all the treatments across the entire population. So that's why we can express that hypothesis in this way. The null hypothesis being that there are no differences among the treatment means across the entire population of treatments. Against the alternative hypothesis that sigma squared sub tau is greater than 0, and that is equivalent to saying in words that differences do in fact exist among at least some of the treatment means in the population of treatments. Now, for both the fixed treatment effects model and the random treatment effects model, the rejection rule is to reject the null hypothesis if the test statistic, F sub t, that F statistic for treatments, is greater than the upper alpha percentage point of the F distribution with p minus 1 numerator degrees of freedom and denominator degrees of freedom equal to p minus 1 times p minus 2. So this is a good place to stop this particular lecture video. We'll pick up the next lecture video talking about evaluating the effectiveness of the Latin square design.